Hello everybody, my name is Aleš Kuchas and now I'm going to discuss whether or how northern stratospheric polar vortex could be modulated by the Hunga eruption, which happened in January 2022. If you'd like to read more, you can reach our preprint available at Edusphere in a letter format. Here I would like to motivate our study. Based on this figure from Milan et al. 2024, I would like to document during the first years after the eruption, there is still a significant amount of original eruptive water vapor in the stratosphere, either observed by MLS or modeled by various models. By looking at the time series of zonal winds at 10 hectopascal and 60 degrees north, which is a typical metric to examine stratospheric polar vortex, you can get an idea of whether the stratospheric polar vortex is really strong and stable or weakening to pass into its southern stratospheric warming moves. Interestingly, both post-Hunga Tonga winters experienced southern stratospheric warmings, and actually two major SSWs has been detected in 2024. In our study, we mostly use so-called ESM. However, we use observations to verify our model simulations. As I said, we use so-called version 4 ear system model, which couples Max Planck Institute ear system model with chemistry and aerosol microphysics. This provides us perfect tool to study impacts of Hunga Tonga eruptions. For details, I refer to Sukurilov et al. 2021. We run fully free running Tanzan setup with 5-year spin-up prior to Hunga Tonga eruption, which secures us the fully diverged ocean and atmospheric state. We've got 10 ensemble members with and without the Hunga Tonga forcing, which includes both aerosols and water vapor. In the following plots, I will always plot anomalies expressing differences between the simulation with and without the Hunga Tonga forcing. As you can see here, in our simulation, we are able to match the stratospheric water vapor mass measured or estimated in observations or in M2 screen analysis. And this is given the trick that we switch off the water freezing around the emission region. Other model simulations erupted several times more of water vapor to match the MLS estimate of 150 teragrams. Let's look at our results and set the scene and show how water vapor and aerosols evolves in time, and that our model is doing reasonably well compared with observations. As you can see by the contour lines, water vapor plume extends horizontally, firstly towards the polar vortex in southern hemisphere and then across the equator. Before DJF in 2023 dispersed into northern hemisphere and above the star poles. Aerosol plume evolves similarly towards the southern hemisphere, as you can see by the brown shading and lower pressure levels. Here I would like to illustrate the evolution of the monthly zone mean structure of ozone, in upper part, OH in middle part, and temperature below for the extended winter 2022 and 2023. The excess of H2O increase the OH radical, causing a negative global ozone response in the upper stratosphere and lower mesosphere due to the increase of the hydrogen ozone loss, and a small positive ozone response in mid-stratosphere due to the interference of the NOx catalytic cycle by the addition of OH, right? In the lower mesosphere, the negative ozone anomaly is a direct consequence of the chemical pathway initiated due to the excess of OH. Note that significant OH anomalies similar to those of ozone at the time do not reach the pore cap. Radiatively induced anomalies in temperature emerge in our simulations around and above the stratopause as a consequence of the reduced absorption of ultraviolet radiation by ozone. The negative mesospheric temperature anomaly emerges at the beginning of boreal winter and extends up to the 20 degrees north. In March 2023, we observed increase in polar temperature, as you can see here, and increase polar ozone concentrations, as you can see here. This is connected with the modulated stratospheric polar vortex, as shown in details in the following daily plots. Negative temperature anomaly at lower latitudes in lower mesosphere persisted through the whole winter, in contrast to no persistent temperature anomaly at higher latitudes. This difference between low and high latitudes results in a reduced meridional temperature gradient, which via thermal wind relation weakens the winds. In consequence, weakened winds allow more planetary waves to propagate upward, further disturb the vortex, and the slowdown of the vortex is associated with this polar warming connected with enhanced Burden-Upson circulation, which, as you could see, resulted in increased ozone concentrations. It shows also the plot below the transition from more positive to more negative northern annual mode values, therefore from stronger to weaker stratospheric polar vortex associated with enhanced upward propagation of planetary waves, represented here by the added heat flux at 100 hectopascal, as shown by the green line. The vertical drips of negative NAM values becomes apparent, which suggests that stratospheric anomalies are triggering some of the changes observed in the troposphere in April, right over here. We can explore these conditions at the surface further. Negative NAM is also apparent at the surface in April, following the stratospheric anomalies shown before. We identify positive sea level pressure in polar latitudes and negative sea level anomaly in mid-latitudes. This pattern is characteristic of a weaker stratospheric polar vortex and is associated with an equatorward shift of the tropospheric jet stream. The canonical pattern with the pronounced cold anomaly in Northern Europe clearly arises for this weak vortex event. To conclude, I demonstrated a novel pathway linking water-rich volcanoes such as Hunga Tonga to surface climate anomalies via modulation of stratospheric polar vortex. I summarize here the mechanism of in the displayed diagram, where the major aspect is played by the reduced meridional temperature gradient in both. This mechanism provides, in summary, a chain of processes which could have contributed to the observed SSW in 2023 or 2024 or both. This we couldn't fully attribute. If you have further questions, please get in touch via the AGU app or email me. Thanks for your attention.